Hello everyone, I'm Hariharan. I'm a postdoc at the Arizona State University. I'd like to first thank the organizers for including a lightning talk section in the conference. I'll be very briefly describing a real-time radio visit that I'm currently working at the ASU. As you can see, it's a collaborative project involving multiple people across various institutions. The imaging algorithm is called E-field parallel imaging correlator or EPIC that is described in detail in Tyagarajan et al. 2017. It is based on the modular optimal frequency Fourier mathematical formalism for direct Fourier imaging. The MOF is described here in the flowchart. The time domain voltages from individual antennas, which are a measure of the electric field incident on the antennas, are first Fourier transformed to frequency domain. The frequency domain voltages are then delay calibrated and gridded onto a UV plane. The UV gridded voltages are then Fourier transformed, squared, and integrated to get the final image. We find that the EPIC is computationally much more efficient as compared to an FX correlator, particularly for real-time imaging in large N dense arrays like Hera, Hirax, etc. We have a GPU architecture of EPIC that is described in this block diagram here. It consists of multiple modules implementing various functionalities like delay calibration, voltage gridding, and squaring and accumulation to get the final image. The GPU architecture was first deployed and tested in one of the LWA stations at Sevialta National Park that is described in James et al. 2019. LWA Sevialta is a compact array of 256 antennas in a pseudo-random arrangement with an aperture of approximately 100 meters, and it operates in the frequency range of 10 to 88 MHz. The initial deployment of EPIC had an instantaneous bandwidth of 400 kHz per GPU per node, and we have 2 GPUs per node. So we have been working on performance optimizations to improve the real-time operating bandwidth. And in the current version of EPIC, it can process a bandwidth of approximately 2.5 MHz per GPU. Here we have a snapshot image of the sky with a bandwidth integration of 250 kHz and a time integration of 250 milliseconds. And the waterfall diagrams represent the dynamic spectrum extracted from a sequence of images over a period of 10 minutes. The top panel shows the dynamic spectrum of an empty region of the sky that is marked E in the image, and the bottom panel shows the dynamic spectrum of the sun. And the enhanced features are basically solar activity. So we're still working to include additional features to the EPIC, like RFI mitigation and transient detection, and we want to improve the bandwidth performance to approximately 20 MHz per node. And we are looking to implement EPIC on LWA to follow up some of the strong pulsars and known FRB repeaters. So if you're interested in this work, please reach out to me and we can have further discussions on this. Thank you.